In this video we are going to look at a way in which complex numbers can be represented geometrically. This geometric representation, which is called the Argand diagram, starts with what looks like a very normal pair of axes, except the x-axis has been labelled real and the y-axis has been labelled imaginary. And then we use the point 4,2 to represent the complex number 4 plus 2i. And similarly, we use the point -3 minus 1 to represent the complex number -3 minus I. And in general, we use the point PQ to represent the complex number P plus IQ. So the Argand diagram is a very simple means of illustrating complex numbers. So in this Argand diagram we've got 3 points representing the complex number Z1, which is 1 plus I, Z2, which is 3 plus I, and Z3, which is 3 plus 2i. And we've formed a triangle using those three complex numbers. Now let's see what happens if we transform each of these z values using the rule the original z value becomes the z value add -4 plus 2i. So 1 plus I is going to move to the point which is 1 plus I add -4 plus 2i, in other words -3 plus 3i. Similarly, Z2, which was 3 plus I, is going to end up being -1 plus 3i. And Z3, which was 3 plus 2i, ends up moving to -1 plus 4i. So our original triangle has been moved to the new red triangle. And we can see easily that adding -4 plus 2i to a complex number, that's an arithmetic operation, is corresponding to a translation of -4, 2, which is a geometric statement. So addition of complex numbers corresponds to translations of shapes in the Argand diagram. Now let's have a look at what happens if we take a complex number and we multiply the complex number by 1.6 plus 1.2i. So here we've got the output from GeoGebra illustrating this rule. Z goes to 1.2 plus 1.6i times Z. Okay, we're calling the complex number 1.2 plus 1.6i the complex number W. So first of all, notice that I've got W plotted towards the bottom of the diagram, and that we can see that the complex number W is 2 units away from the origin, and that if we look at the angle made by the positive real axis at the origin and the line going off from the origin to W, then that angle is 0.927 radians. Our object triangle is the blue triangle, whose vertices are Z1 equals 3 plus I, Z2 equals 6 plus I, and Z3 equals 6 plus 5i. The brown image triangle is obtained by taking a Z value and multiplying that Z value by W. So for example, to obtain the image of Z1, we take Z1, which is 3 plus I, and we multiply it by W, which is 1.2 plus 1.6i. So we've got the image of Z1, which is labelled as Z1 dash, is 1.2 plus 1.6i times by 3 plus I, which gives me 2 plus 6i. And we obtain Z2 dash and Z3 dash in exactly the same way. Now the first thing I want you to notice is that the sides in the brown triangle are twice the size of the corresponding sides in the blue triangle, which suggests that in moving from the blue triangle to the brown triangle, there is certainly an enlargement involved. And since the sides are twice as long, that enlargement must be an enlargement of scale factor 2. So let's just add a third triangle to our diagram, which is simply the image of the blue triangle after an enlargement of scale factor 2. So there's my image of the blue triangle after an enlargement of scale factor 2. To move that enlarged triangle onto the brown triangle, we clearly need to do a rotation. The rotation we can see by going one point at a time. It doesn't really matter which point we take, so I'm taking in fact Z3 and see where its image after the enlargement ends up after the rotation. And we can see that it's turned through an angle of 0.927 radians. So, what has happened is that the operation Z goes to 1.2 plus 1.6i times by Z can be interpreted geometrically as an enlargement of scale factor 2 and centre the origin, followed by a rotation of 0.9273 radians, or 53.1 degrees if you like, anti-clockwise about the origin. And notice that the enlargement scale factor was exactly the same as the distance of W away from the origin, and that the angle of the rotation was exactly the same as the angle made at the origin by the positive real axis and the line off to W. Let's now have a look at a similar case where we're taking again a multiplication rule, and this time the multiplication rule is Z goes to minus 0.7 plus 2.4i times by Z. So here again is the GeoGebra page for this transformation. Again, initially, the first thing to observe is that we have got W is this time 2.5 units away from the origin, and the angle made at the origin by the line in the direction of the positive real axis and the line off to W is 1.854 radians. Now again, our object triangle is formed by the complex numbers Z1, Z2, Z3. Our image triangle is obtained by just multiplying each of the Z values by W, which is minus 0.7 plus 2.4i. And we can see that the lengths of the image triangle are all 2.5 times the lengths of the corresponding sides of the object triangle. So, in moving from the blue triangle to the brown triangle, we've certainly got an enlargement to scale factor 2.5 together with a rotation. So we'll add an enlargement of the original triangle with scale factor 2.5 to the diagram, which is there. And then if we consider the image of Z3 in the enlarged triangle and the image of Z3 in the brown triangle, we can observe that the angle that Z3 has turned through is 1.854 radians. So the arithmetic operation Z goes to minus 0.7 plus 2.4i times Z can be interpreted as an enlargement to scale factor 2.5 and centre the origin, followed by a rotation of 1.854 radians anticlockwise around the origin. Now we'll be coming back to this result later on because it's going to be very useful to us. In the first place, it's useful because the enlargement of the scale factor was the distance of the complex number from the origin. And this distance of a complex number from the origin is called the modulus of the complex number. So the modulus of a complex number is the length of the line joining the origin to the point AB, which represents the complex number A plus IB on the Argand diagram. And we know how to work out the distance between the origin and a point on our Cartesian plane. It's simply the square root of a squared plus b squared. So the modulus of a plus ib is the square root of a squared plus b squared. So the modulus of 4 plus 3i is the square root of 4 squared plus 3 squared, which is 5. And the modulus of minus 5 plus I is the same thing as the modulus of minus 5 plus 1i. So that is the square root of minus 5 squared plus 1 squared, which gives us root 26. Now the argument of a complex number is the angle made at the origin by the line that goes off in the direction of the positive real axis and the line that goes off to the point representing the complex number. So the argument is the anti-clockwise angle which OA makes with the positive real axis. So there's the line OA, there's the positive real axis, and there's the angle which is the argument of Z. The argument of an angle is usually given in radians, not in degrees. And there are two conventions that are used. Either the argument is given as an angle between minus pi and pi, or alternatively the argument is given as an angle between 0 and 2 pi. If it matters which of these two conventions you're going to use in a question, it will be clear from the question which convention is required. So we'll now move on and we'll try and work out the modulus and the argument of some complex numbers. The modulus is easy, it's just a question of working out the square root of a squared plus b squared. The argument is a little bit trickier, and the best thing you can do with the argument is always to draw a quick sketch diagram and then use a little bit of trigonometry. So for the modulus and argument of 1 plus root 3i, the modulus is nice and straightforward. It's simply the square root of 1 squared plus root 3 squared. So that gives us 2. And then for the argument, we have a right angled triangle set up with a adjacent side of 1 and an opposite side of root 3. So we've got tan theta is equal to root 3 over 1, which means that theta equals pi by 3. So we can say that arg z is pi by 3. For the second example, we've got to find the modulus and argument of minus 2 plus 2i. So again, the modulus is nice and easy. The modulus is simply the square root of minus 2 squared add 2 squared, which gives us the square root of 8, or 2 root 2. For the argument, we need to remember that we measure the argument from the positive x direction at the origin and off to the point representing the complex number. So in this case, the argument is on an obtuse angle. So what we're going to start off by doing is working out the acute angle in this triangle. And this triangle has got a side of 2, an opposite side of 2, and an adjacent side of 2. So we've got tan theta equals 2 over 2, or theta equals pi by 4, which means that the argument of z is pi minus pi by 4, which is 3 pi by 4. For our next example, we've got to find the modulus and argument of minus 3 minus 2i. The modulus again is nice and easy. It's simply the square root of minus 3 squared add minus 2 squared, so that's the square root of 13. The argument, we need to measure the angle from the positive real direction round to the line joining O to the complex number. So we might try and find alpha first of all. So if we try and find the angle alpha, well, alpha is an obtuse angle. We can find the acute angle rather by setting up a little triangle, and we've got tan theta is 2 over 3. So theta is 0.588 radians. That means that alpha is pi minus theta, which gives me 2.544 radians. Now, the argument is the anti-clockwise angle from the positive real axis round to the line joining O to the complex number. So if we are going to use alpha to give us the argument, we would need to say that the argument of z is minus 2.544 because it is a clockwise angle of 2.544. And that answer would be fine if we are working with the convention of giving arguments between minus pi and pi. If on the other hand we're insisting on using arguments between 0 and 2 pi, then the argument we require is the angle in green, which is pi plus theta, which will give us something approximately 3.73 radians. Now if we look back at the previous two slides, we can see that if we multiply by 1.2 plus 1.6i, then that was equivalent to an enlargement of scale factor 2, and 2 was the modulus of 1.2 plus 1.6i, followed by a rotation of 0.273 radians anti-clockwise about the origin, and 0.9273 was exactly the same as the argument of 1.2 plus 1.6i. And similar result held when we had the second transformation, multiplication transformation. So, if we've got the operation z goes to w times z, then the geometric effect is an enlargement of scale factor modulus of w and centre the origin, followed by an anti-clockwise rotation of the argument of w about the origin. Now, just need to remember something important about the definition of trigonometric functions. If we start with a circle of centre the origin and radius 1 unit, and then we draw a ray coming out from the origin, from the centre of the circle, making an angle of theta with the x direction, then the x-coordinate of P is the definition of the cosine of the angle theta, and the y-coordinate of P is the definition of the sine of the angle of theta. Now, keeping this in mind, we're going to find a way of working from the modulus argument form for a complex number back to the xy form of a complex number. So, let's suppose that we've got a complex number z which has got a modulus of r and an argument of theta. Then that means that the point z lies on a circle of radius r and centre the origin, and it also means that the angle at the origin made by the positive real direction and the line going from O to Z is equal to theta. Now, what we've also shown on that diagram is the circle with centre 1, sorry, with centre the origin, but with radius 1. And we've shown the point P where that circle meets the line joining O to Z. Now, from what we've just said, the coordinates of P must be given by the x-coordinate of P is cos theta and the y-coordinate of P is sine theta. That simply follows from the definitions of cosine and sine. Now, we can move the circle of centre the origin and radius 1 onto the circle of radius r and centre the origin by simply doing an enlargement of scale factor r. And if we carry out an enlargement of scale factor r, then the point P will move on to the point Z, and the point Z will therefore have coordinates r cos theta, r sine theta, which means that the complex number that the complex number form for Z must be Z equals r cos theta plus I times r sine theta, or equivalently Z equals r times by cos theta plus I sine theta. Now, this is an important result, and it's also useful to have a shorthand for this result. If Z is a complex number with modulus of Z equals R and argument of Z equals theta, then we'll sometimes summarise that by writing Z equals square brackets R comma theta. So our last result now becomes, if we know that Z has a modulus of R and an argument of theta, then z is equal to r cos theta plus ir sine theta, or r times cos theta plus I sine theta. Now, I've got to find a complex number whose modulus is 8 and whose argument is minus 2 by 3. Well, the result that we just had told us that if we know that we've got mod z equals r and arg z equals theta, then we know that z is r lots of cos theta plus I sine theta. So in this case here, our complex number must be z equals 8, that was the modulus, times by cos of minus 2 pi by 3 plus I sine minus 2 pi by 3. If we remember that cos of minus theta is always the same thing as cos theta, and that sine of minus theta is always the same thing as minus sine theta, we can rewrite that as z equals 8 cos 2 pi by 3 minus I sine 2 pi by 3. Using our calculator, or from our knowledge of the exact forms of trigonometric functions, cos 2 pi by 3 is minus a half, and sine of 2 pi by 3 is root 3 upon 2. So we've got z is 8 times by minus a half minus I root 3 upon 2. In other words, z is minus 4 minus 4 root 3i. So if we know the modulus and argument of a complex number, it is fairly straightforward to work out what the complex number is in its x plus iy format. Now at this stage, it would be worth your while, please, pausing the video and just have a go at these two questions, which just assess whether you've got the basic idea of the modulus and argument of complex numbers, and also the basic idea of working back from the modulus and argument to obtain the complex number in the form x plus iy. When you've done these two questions, continue with the video and you'll obtain the answers. So there are the answers for the two questions that I hope you've had a look at. I hope you've managed to get most of them right. And now there's just one final thing we want to have a look at in this video. If we've got w is cos b plus I sine b, then that certainly means that I've got w is 1 times cos b plus I sine b, so the modulus of w must equal 1, and the argument of w must equal b. Now from what we saw earlier on in the video, the operation z goes to w times z has the geometric effect of an enlargement of scale factor mod w, followed by a rotation anticlockwise of arg w. Well, an enlargement of scale factor 1 just leaves z entirely alone. So all we've got is that multiplying by little w here is simply going to give us a rotation of b anticlockwise around the origin. So if I start off with the complex number z and multiply it by cos b plus I sine b, then that gives me an anticlockwise rotation of angle b about the origin. And in an entirely similar way, if I start with z and multiply it by cos a plus I sine a, then the effect of that is simply going to be to give me a anticlockwise rotation of angle a about the origin. Now consider what happens then if I first of all multiply z by cos b plus I sin b, and then multiply the answer by cos A plus I sin A. So the first multiplication gives me an anticlockwise rotation of angle B. The second multiplication gives me an anticlockwise rotation of angle A. So altogether, that must be the same thing as doing a single anticlockwise rotation of angle A plus B. But we know that that can be represented by simply multiplying z by cos of A plus B plus I sin of A plus B. So looking at these two results, we've just seen that the process of going from z to cos A plus I sin A times by cos B plus I sin B times z is going to be exactly the same as going from z through to cos of A plus B plus I sin of A plus B times z. In other words, we're saying that cos A plus I sin A times by cos B plus I sin B must be exactly the same as cos of A plus B plus I sin of A plus B. Now we can multiply out the right-hand side. So multiplying out the right-hand side, we've got cos A cos B plus I times cos A sin B plus I times sin A cos B plus I squared times sin A sin B. Remembering that I squared is minus 1 means that we've got cos A cos B plus I times cos A sin B plus sin A cos B minus sin A sin B. So collecting together the real terms and the imaginary terms, we've got the real term is cos A cos B minus sin A sin B, and the imaginary term is cos A sin B plus sin A cos B. Now on the left hand side, the real term is cos A plus B. On the right hand side, the real term is cos A cos B minus sin A sin B. So we must have cos of A plus B is the same thing as cos A cos B minus sin A sin B. Looking at the imaginary terms on each side, we've got sin A plus B must be the same thing as sin A cos B plus cos A sin B. Notice I've just switched the order around in terms of the two imaginary terms on the right hand side. So what we've got there is we've got a complex number justification of a result that you may have already met, known as the compound angle formulae. And we're going to need the compound angle formulae in our next video, which is why we needed to have seen them in this video.